which appeared in August. So yeah, so let's just consider a general quantum many-body system. Say, let us imagine it started from initial state is some far from equilibrium pure state. Then for generic system, such a state will eventually thermalize on the time evolution. And so generically we approach equilibrium. And when it approaches equilibrium, it's actually very hard to tell from local measurements whether this is a pure state or just density operator. And this is actually precisely the situation we face in the evaporation of a black hole. So when a star, say, imagine you have a star originally in the pure state, which collapses to form a black hole, and then eventually evaporates. And say, if the initial state is a pure state, then throughout the process, the system should still be in the pure state. But the black hole evaporation appears like a purely thermal. And so naively, according to Hawking, the information has lost. And so the key question is how to actually understand that actually black hole remains to be in the pure state. So Page had a very simple proposal, more than 20 years ago. Yeah, he pointed out, say, if you look at, say, entanglement entropy or Renyi entropy of the system, say, if you consider a subsystem A, and then if the system is in the pure state, then say the Renyi entropy will be equal between the system A and its complement. So the complement, which I call A bar. And so n equal to 1, you should understand as a volume entropy, and then higher integers, just the Renyi entropies. But for general a mixed state, this is not satisfied for mixed states. So if one can calculate, say, entanglement entropy or Renyi entropies of a system, for example, a black hole system, in particular, say, the radiation from the Hawking radiation, then one should be able to tell whether the system is in the pure state or it's in the mixed state. But in general, it's very hard, say if I give you a quantum many-body system, it's very hard to calculate either Renyi entropies or entanglement entropies. So standard trick, which works, which applies to a finite dimensional Hilbert space, is to you try to calculate the average of all pure states. Okay, so you look at the Renyi entropy for given states, and then you average over all possible pure states. Yeah, all pure state of your system using the hard random measure. And since the original quantity obeys the unitarity constraint, when you do the average, still satisfy the unitarity constraint. And then the famous result, say, started from Lukin and then Sasnoid and Page, is that when A and the A bar are not very, say, close to each other, say if they're one of them is much bigger than the other, then you get a very simple result. Say you find the entropy just given by the minimum between the log of the dimension of the Hilbert space, say either log dA or dA bar. Okay, so this gives you very powerful a result in thinking about the give you lots of intuition and about what can in general happen, say for system with a finite dimensional Hilbert space. And then Page used this result to make the prediction for the Page curve of the black hole evaporation, which can be used as a very strong check of the unitarity of the black hole evaporation. So so this result gives much intuition for what to expect in actual physical systems, but actually does not really help with actual calculations. Say if I give you a system with a fixed Hamiltonian, and with a given initial state, and then this result can only be thought as somehow. Then you have to make some assumptions. So you have to assume that the state somehow evolved into a typical state, so that you can apply this average result. And also, this average result applies to case which to situations which energy constraints are not important. Say when the system is at a finite temperature, or there's a strong energy constraint, or if you have an infinite dimensional Hilbert space, or in field series, and then then such a result does not apply. So the plan of my talk is I want to describe a method to calculate the entanglement entropies of an equilibrated pure state, which I will explain what this means, and without the need of doing average or assumption of typicality. And so this result, this method can be considered as computing the leading term, say, of an approximation, which can in principle be improved on. And so this method can also be applicable to finite temperature, infinite dimensional Hilbert space, and the field theory, etc. And also the answer can be expressed solely in terms of properties of an equilibrium density operator, and independent details of initial state. Okay, but it's actually compatible with unitarity. And then you can apply this method to gravity systems, and then this provides a way to obtain answers, say, be consistent with unitarity using Euclidean path integrals. So as an example, I will give a systematic derivation of replica wormholes introduced recently in discussing this black hole evaporation, including elucidate their mathematical origin and the physical nature, and why they are without compatible with unitarity. So far, this discussion of the replica wormhole was considered to be somewhat ad hoc or prescription. It's not very clear somehow why it gives the correct answer, why it gives the answer compatible with unitarity. But we will see actually this naturally follows from the approximation I'm going to describe. And then I will conclude with some discussions. So if you have some questions, please don't hesitate to ask. Good. So let me first describe the setup of the problem. So let's consider you start with the initial pure state psi 0, and then on the time evolution, say to some final state. So let's say the time evolution operator is given by u. So we will assume that this u corresponding to sufficiently long time that the system has equilibrated. Yeah, so macroscopically appears as a thermal equilibrium. Okay, and so we call this psi an equilibrated pure state. And so for such just from our normal experiences, if you have equilibrated system, then we can approximate such system by some kind of equilibrium density operator. And let's just suppose there exists some kind of density operator rho e, and which I write it as an unnormalized operator, which is I alpha, and then the partition function of then the trace of I alpha, which I call z alpha. And then so this z alpha, which is the trace of the I alpha, can be considered as an effective dimension. And so alpha, say, denotes the equilibrium parameters such as temperature or chemical potential, etc. Okay. And so for example, when we say a system have, say, approach equilibrium, so that means you can associate some dynamical quantities with such a system, say like entropy, free energy, etc. And then the free energy or entropy of such a pure state then can be approximated by that of this density operator. Okay. And so here now let me give you some examples. So if you have a system which with finite dimensional Hilbert space, and there's no energy constraints, and then the system can be considered to equilibrate to infinite temperature. So in this case, the I will be just identity. And then the trace of I, then of course, will be just dimension of the Hilbert, dimension of your Hilbert space. But if you consider, but if your say initial system have some finite energy range, say for example very narrow energy range, then you can try to approximate it by a macro-canonical ensemble, and then ZE would be just the dimension, yeah, of the of this energy gap, of this energy window of which you define your macro-canonical ensemble. You can also define canonical ensemble.
Sorry, a question. So your time evolution operator U is an arbitrary time evolution operator, or is some special class of U's, for example, satisfying summarization hypothesis?
Yeah. That's right. We assume that. So we assume that this. We assume that the system actually equilibrates. Yeah. So this U must be such that the system actually equilibrates. Yeah, but that's the only constraint.
So this U is a special class. It's not general U. It's a special class of.
Yeah, I would say U is pretty general because most of essentially all systems in nature they appear to thermalize. They are very special systems. Say for example, certain integrable systems or these many body localized systems. Maybe they don't thermalize. Yeah, but generic systems, they do thermalize. So this is pretty general.
Okay.
Good. Yeah.
So I have a question. So this is not from TDD. So but do you assume that U is still unitary or not?
Yeah, U is unitary. Yeah.
Okay.
Right. Yeah. So let me just emphasize. The density operator come from this psi. Of course, it's very different from this equilibrium density operator. It just various properties of this psi can be approximated by such equilibrium density. Yeah, just say if you look at the gas in the room, suppose the gas is initially in the pure state. When we make local measurement of this gas in the room, we measure its temperature, we can measure its correlation functions. We cannot really tell that's come from a pure state. We will very well just describe it by some kind, for example, using canonical ensemble. Yeah, that's just the sense.
So you also assume that locally, actually, you can always arrive at equilibrium state, right? Locally.
Yeah, that's right. Yeah,
okay.
yeah,
okay,
yeah. Say if you measure some few body observables, and then they appear to be in thermal equilibrium. Yeah.
Okay.
I am a bit confused. So by what you are saying, if I start from a pure state, I'm going to have my time evolution to make it look like an equilibrated pure state. So it should look like locally, or like it looks close to a thermalized state. I am not sure like how to have like a general U to make a pure state look like a thermalized state.
Yeah, right. So we actually expect generic non-equilibrium system, non-integral system. The U for general non-integrable system, they should all be able to do this. Yeah, just as say if you consider the gas in the room, let's just take it to be, say, take all the molecules of the gas to be, say, in one corner of the room, but with sufficiently high energy, but it's in the pure state, and then you let it evolve, then all the molecules will fill the room, and when you make whatever your daily measurement, that gas will appear as a thermal state, and you will not tell. It's very hard to tell the difference between just from making some local measurements to tell the difference of that gas, say from a density operator. Yeah, even though it remains a pure state. Yeah, because of the unitarity of quantum evolutions always remains a pure state.
One more other question from a student, please.
Okay. Yeah, Professor. So yeah, I actually have about the same question because it seems that you want to state a equilibrated pure state is a state after sufficiently long time. When you do measurement on the local observables, it produces the same result as the like mixed state, the ensemble. So what kind of observables you get for what kind of observables you get the same result? Local observables, any other requirement? And another question is the mixed state approximation, unique?
Yeah, that's a very we normally say this happens for the few body operator in the following sense. Say if you only observe say if the observable you use to probe the system only probe a very small fraction of the system, and then you should not be able to tell whether this is a pure state or density operator.
Okay.
And and then the second part of your question, can you say it again? I forgot the.
Sorry, is the so basically we know it's a pure state by unitary evolution, but somehow when you measure the local observable, it's indistinguishable from some like mixed state or density operator. Is the density operator equivalent density operator or mixed state unique?
Oh yeah, right. Yeah, that's a very good question. For example, if you just make local measurement, say if you make the say measurement, say if you only observe a very let's consider the following picture. Say if you observe only a fraction of the system, that's let's say the subsystem you probe is fixed in size, and then you take the thermodynamic limit. That means that the subsystem you probe is the approximate measure 0 compared to the full system. In that limit, then you will not be able to tell the difference between the macrocanonical ensemble and the canonical ensemble. As normally in statistical physics, in the thermodynamic limit, you cannot tell the difference. But when you're away from thermodynamic limit, then you can actually tell the difference between macrocanonical and the canonical ensemble. So I would say for most questions, it should be unique, but in certain limit, you may not be able to tell the difference. Yeah.
Okay, thank you.
Mm-hmm. Good. Yeah, so I want to emphasize this is precisely the situation we encounter in black hole physics. So when black hole evaporates, emit Hawking radiation, and for all purpose, the Hawking radiation behaves like really thermal. Okay, it's no matter how you measure Hawking radiation, it just appears as thermal. And but of course we know in the end all the Hawking radiation together, if the information, if the evolution of the black hole preserves unitarity, then all the radiation together should still be a pure state. And but if you just look at small portions of Hawking radiation, it's always thermal. Yeah. So this is the same issue. Yeah. Good. Yeah. So this notation I alpha will appear over and over. Just you should keep in mind that this is the unnormalized equilibrium density operator, and its trace defines the effective dimension for us. And then we'll always take this effective dimension to be very large. Okay. And so we consider many body systems. So and the quantity we are interested in is Renyi entropies. And actually, I will mostly talking about this Renyi partition function. So essentially the exponential of the Renyi entropy, which is defined by you take your initial density operator, which is a pure state, you evolve it with time, then you take trace over the complement A bar, then you take power n. So this defines your Renyi entropy. Yeah, Renyi partition function. And when you take the logarithm, you get the Renyi entropy. So yeah, you can write this expression in terms of path integral. And so each u then corresponding to a path, say from 0 to some time t, which is defined by the u. And then here you have u dagger to the power n. So actually, when you write it in the path integral, there are 2n contours, okay? And n of them going forward in time corresponding to u, and n of them going backward time, which corresponding to the u dagger. And then the initial state of this path integral is rho 0, and the final states essentially are specified by these trace conditions. So you first take trace a bar, and then take power n, and then take trace a, okay? And yeah, so and the integrand of your path integral will be just given by your action, by your standard action, but there are 2n copies of them. So the one with forward in time, you have the positive I, and then one for your dagger, then you have the minus sign because you take the dagger. Okay. And yeah, again, this rotation will be used over and over, this Renyi partition function. Just keep it in mind. Good. So here, let me give you a heuristic argument for what kind of sub-configuration we expect to be important in the long time limit. So if you look at this expression, and say if you consider the, say, typical many-body system, and for the time sufficiently long that you approach equilibrium, then you expect the this S to be not very small, okay? And and then when you take exponential I, so you expect this exponential to be highly fluctuating, okay? And highly fluctuating, so typically the average to 0. But there's a special subset of configurations corresponding to that the phi along the positive contour and along the negative contour, they just relate by some permutations. Okay, so phi it equal to phi prime. So phi prime corresponding to the path integral configurations for the path integral going back in time. So if you take phi and phi prime to be just related by permutations, okay? So sigma is the element of the permutation group. And if you are related just by permutations, and then these two sum will be the same because it's just the same configuration reshuffled. And but the sum that don't care about that. And then this exponential, then the argument for this exponential will be identically 0. Okay. So for this special subset of configurations, and actually there's no phase factor. Okay. So intuitively, you may expect they dominate the path integral in the long time limit. Okay. Yeah. So in particular, for such kind of configurations, because the exponential completely cancel, the argument for the exponential completely cancel, actually the final the contribution from this subset configurations will be time independent because the time dependence actually comes from this integrand. Okay. And so these subset configurations you expect. And then they lead to time independent expressions. And that's also intuitively fits with what we expect when the system approach equilibrium, and then the whatever physical value should not change. Okay. But I emphasize this is only a heuristic argument. But this heuristic argument, and that suggests importance of the somehow the permutation group may play important role in finding a way to approximate, to find the leading order contribution to such Renyi partition functions. So any questions on this? Good. Good. So so now let me try to make this intuition precise. Okay, so this is only a intuitive argument. So now I will introduce a formalism to make this intuition precise. and they try to develop an approximation procedure motivated by this heuristic thinking. Again, so if you look at the path integral for this Renyi partition function, you may consider it as a transition amplitude in 2n copies of your Hilbert space. Okay, so intuitively, you can already intuitively see this from the path integral. This path integral contains 2n copies of the path integral of the original system. Okay, and so you may imagine somehow mathematically extend this rho zero into a state into 2n copies of your Hilbert space, and then the evolution operator will be just u times u deck to the power n. Okay. And we can make this precise, and you can in fact write this Renyi partition function in the following form, and the rho 0e and this eta. Yeah, I will explain what this notation means. But for the moment, let me just say there are some states in the 2n copies of your original Hilbert space. Okay, and so this rho 0e is related to your initial density operator, and this eta and this final state are related to how you take the trace. Okay, how you take the trace to get the Renyi entropy. Okay, so the next slide will be a little bit notation heavy. So if you have any questions, just please do ask. So for any operator, yeah, let's first introduce a general definition. So for any operator acting on your original Hilbert space, we can define, oh, what happened? We can define a set of n factorial states, okay? And each n factorial state associated with the element of the permutation group as the following. So with operator O, we can define n factorial states, and each of them associated with the element of the permutation group Sn, which belongs to 2n copies of your Hilbert space. So if I take the original Hilbert space to have, say, basis I, okay, denoted by I, and then 2n copies of the Hilbert space, and I can choose a basis of this form, I1, I1 prime bar, etc. Okay, so I1, I1 bar, yeah, so each of them corresponding to 1 copies of your Hilbert space, and the second copy of H we denote with a bar. Okay, and then there are n pairs of them, and then we can define these states by its overlap with this basis state. And the definition is given by the following: the overlap with this basis state is given by the matrix element of O in the original system, but with the second indices permuted by this element of the permutation group. Okay, and yeah, so for those who have not seen this before, so let me just pause here for a few seconds, and let you take a look at it. And because it may not appear to be very intuitive if you see it the first time. Okay, so let me emphasize, this is essentially a unique definition. Okay, so if you give me the matrix element of O of your original Hilbert space, and then I can just define this state precisely. Okay, yeah, using this matrix element and then the permutation. Okay, so there's a very special state, special n factorial state corresponding to O to be the identity. And in this case, I will just not write O explicitly. Yeah, I will not write identity explicitly. I just denote it by the permutation, by the element of the permutation group. And then in this case, then you just get, yeah, of course, a product of the deltas. Okay, and but the argument of the deltas, again, the second index are related by the permutation. So the basic idea of introducing this kind of notation is the following. So let me give you an example. So say let's take the E to be the identity permutation, and this eta to be a very special permutation corresponding to this cyclic. Yeah, I'm using this kind of cyclic notation for the permutation. And so, for example, this notation means that the eta corresponding to you take n goes to n minus 1, n minus 1 go to n minus 2, 2 to 1, and 1 to n. Okay. So suppose let's take E and eta, and then for O associate with E, and then overlap with E, then what you get is just trace O to the power n. If I take O, the state O with the identity permutation, and overlap with this eta, the state corresponding to the identity operator with eta, and then you find just trace O to the power n. Okay. So the basic idea is that this kind of definition gives you a very convenient way to introduce all kinds of trace structure, say associated with the operator. Okay. So by choose this permutation and of your initial state and the final state, then you can get all possible trace structure of O. And that's what we want in order to write down the Renyi partition function. And because the Renyi partition function corresponding to a specific size of trace, and so so here you take the trace A bar on this quantity. So you just take the E, the identity element, to be associated with A bar, but then the eta associated with the subsystem A. Okay, and then the initial state you take the 0. The 0 is the operator, and then the state corresponding to the identity. Good. Any questions on this? Anyway, if this is too heavy, don't worry, and just keep in mind that we can write this Renyi partition function in terms of the transition amplitude in this replica space. Okay, in these 2 entropies of the replica space. Okay, so now I'm going to introduce the approximation we are going to use. But before doing that, let me introduce one more piece of motivation. So when you consider, say, let's imagine if you have a finite dimensional Hilbert space, okay, and so we are interested in this quantity. And as I mentioned, for the finite dimensional Hilbert space, standard technique to do is you average over all possible states. And then it's the same as you average over U with the Haar measure, okay? And then when you average over U, and then actually there's a simple result, is that when you average over U over the Haar measure, what you find is that this quantity which appears, if you average over that, you essentially just average over this quantity. And then you find that this average can be written just as a projection. And this projection is the projection, and P is the projector into the subspace spanned by sigma. So the sigma is the state associated, is the n factorial state, is the set of state associated with the identity in this replica space. Okay. And so in the sense that then the average of this Renyi partition function, then you can just write it as, you can just forget about the evolution, just write it as a projector inserted between your initial states and the final state corresponding to taking the trace. Okay. And so let me just make some comments. So this is a very simple mathematical observation, but it's actually a very powerful one, because that means that the process of taking the average, you can actually rephrase it as a projection to a subset of the states. Okay. So, so doing the average actually then corresponding to you just project into a very special subset of states in the replica space. And in particular, when you say when the system is very large, then the variance is very small. Okay, then the variance away from the average is very small, and then you can actually view this result actually has approximation. For typical Hamiltonian evolution, okay, and so rather than view this as average results, and when you interpret this as a projection, and then you can just interpret it as as approximation, okay, and this approximation is actually very good when the system is very large. And then, and also another important thing is that so this P is the set of state associated with the identity, and in the case with finite dimensional Hilbert space with no energy constraint, the identity operator can actually be viewed as the essentially the equilibrium density matrix. Okay. So this is now can be interpreted as you project into the n factorial states, the space spanned by the n factorial states associated with your equilibrium density matrix. Okay. Yeah, so now I can introduce my approximation. So now I'm consider a more general problem, say for general U and without doing the average, and for system, say can be at finite temperature or even can be field theory. Yeah. Good. So now I will consider
here.
Yeah. Yes.
Yeah. My question is in the equation of Zhou and Nahum, on the right-hand side, do you need to have a limit n tends to infinity?
No, you don't.
So for any n.
Yeah, for any n.
For large n, small n.
Yeah, for any n. Yeah.
For any n, okay.
Yeah.
The average, okay.
Right. Yeah. Of course, we always consider, say, the dimension of the Hilbert space to be very large. You take that to be large first, and then you can take n to be as large as you want. Yeah. But if you have say finite dimensional Hilbert space, say if you have a 5-dimensional Hilbert space, and when you take the n to be very large, and then this may not apply. Yeah.
One question. Here you talk about typicality, right?
Yeah. Here I'm just saying. Here you don't have to talk about typicality. I'm just saying if you want to use this average result, and then you have to use typicality.
So this is not going to be part of your assumption.
No. This is not going to be part of my assumption. That's right. Yeah. Good. Okay. So now I want to motivated by this result, by this reinterpretation of doing hard average over this finite dimensional Hilbert space, and I want to design a scheme which I can actually calculate some leading answer to this Renyi partition function for the general case, okay, described by some general equilibrium density operator. Yeah, so for that purpose, I will just introduce this n factorial states in this replica space associated with this identity operator, with this equilibrium density operator, okay? And so this can be considered as your, say, so this unrenormalized equilibrium density operator, you can view it as, say, as some kind of effective identity. And then you can define the projector into the subspace spanned by this n factorial states. And so those states actually are not orthogonal to each other, so there's a non-trivial metric in this space. But that's fine. Yeah, you can just write down the projector, and then the normalization of the state is given by this Z2. Okay. A normalization of each state is given by Z2. So now you can. So essentially, by definition, because this is come from the equilibrium density operator, and equilibrium density operator is invariant under the time evolution. Okay. And so you can then easily check that because original equilibrium density operator is invariant under time evolution, and the u times u dagger to the power n, okay, acting on these states, leave it invariant. Okay, so you can actually do u dagger or its conjugates. Okay, leave the state invariant. And now we can just split the identity into this P associated with this subspace, and then it's and its orthogonal projection. And then now we can just insert this one into this definition of the Renyi partition function, okay, into both these places. So now because U leave this I invariant, of course, U will also leave the P invariant, okay? And so essentially, when you acting on P, then U just disappear, okay? And then you split into two terms, and one is related to the P, and one is related to the Q, and also the cross term vanishes because because when you acted this on P, and then U disappear. Anyway, just using orthogonal relation between P and Q, and then you find the cross term vanishes. And then our proposal for the approximation is just you keep the P part. Okay, so the Q part in general will be time dependent, but the P part will not. Okay, because for P part, because this property, the U just drop out. Okay, so this is very similar to my earlier heuristic discussion using this path integral when you permute different configurations. And there you find when you restrict to that special set of configurations, and the answer should be time independent. And so here, if you project into this subspace, and then the answer will be time independent. So so now you, so you can just insert P here. Yeah, essentially the only thing for this term, you just will forget about this U and U dag, you just insert P here, okay? Insert this P alpha between this rho 0 and this final state corresponding to taking the traces. And now if we always assume the system is large, in particular effective dimension is large. So in that limit, you can do some further manipulation, which I will not give here. And then you can show that when the system is large, and then for pure, when your initial state is pure, then you can actually simplify that term proportional to P, just this first term, proportional to given by P, further in this form. And actually, so so this is when the Z1 equal to trace I alpha large. And so in this regime, you can further simplify to this form. And in this form, then this actually now is expressed solely in terms of equilibrium density operator. Okay, and now it's independent of initial states. And so there's a couple of line calculations in going from this expression by inserting P here, P alpha here, and to here. But it's not very long. Anyway, so the key thing here is you actually sum over the permutations. Okay, you sum over permutations. So if you take so naive. So when you say consider this system can be approximated by this density operator I alpha, then the most naive thing you would do, say for example, to calculate its Renyi entropy or entanglement entropy, you just use the Renyi entropy or the entanglement entropy of this density operator to approximate it. So that's essentially what Hawking did for the Hawking radiation. For the Hawking radiation, you just treat the Hawking radiation as thermal, and then you just use the entanglement, use the entropy of your thermal density matrix to approximate, say, the entanglement entropy of the Hawking radiation. And that's why you get the result which is not compatible with unitarity. But here the key thing is that you have you sum over permutations. Okay, so the naive equivalent approximation, which you just approximate this by the Renyi entropy of your, say, equilibrium density operator, then that's just corresponding to take tau equal to E. Okay, if you only take tau equal to identity, and then you will get the answer which violates unitarity. So this sum over permutations are very important. Okay, which I will emphasize more later. So first, let me just give you a justification of the approximation. And so for this purpose, I will consider the following quantity. So we'll look at, so in this approximation, we essentially throw away this extra term, ZQ. If you include this Q term, then you actually, then it's the exact answer, okay? So we throw away this Q term. So let's try to estimate the size of this Q term, okay? The term we throw away. So I will estimate the size of this Q term in the self-consistent way, okay? Because of course this term is very hard to calculate. What I will do is I will take the square of this quantity. This quantity is real. If it's complex, then you just take the modulo square. So you take the square of this quantity, and then you apply equivalent approximation to this quantity. Okay. So if this thing is small, and then this should be a very good approximation. Okay. And so this is the basic idea. So this is a self-consistent check. And so this quantity can also be written as this, just the original exact answer, subtract the answer corresponding to the P, which we keep, and then take the square, and then you apply this equivalent approximation. And then also it's related to the difference, which you take the square first, and then do equivalent approximation, or you do equivalent for approximation first, and then the square, okay? Anyway, so the approximation is self-consistent if this delta is much, much smaller than the part you keep, okay, than the part you keep. And this also means, so when this is much small, so this, when this is much smaller than the part you keep, this is also means that this fact, the difference between these two is small. So that means that approximately, whether you do this approximation first to the square, or you first do the approximation and then square, they are approximately equal. Okay, so it means that this approximation can be factorized. And indeed, if you apply this approximation to this computation of the Renyi entropy, then you find that this delta divided by the part you keep is given by this Z1. So Z1 is the partition function. Is your equivalent partition function, and so it's suppressed by the square root of Z1. Okay, so when Z1 is very large, and then this is much smaller than 1. Okay, good. Any questions on this? Okay, good.
So this looks very similar, or maybe the same as just the justification of the typicality. Right, it looks similar calculation.
So
you have other.
Yeah, right. So in the case, in the case which, so this is a generalization of that. So in the case, if you say in the case of the, say for example, when you go to the finite dimensional case, so in the finite dimensional case, then you can keeping this this ZMP. Then corresponding to you just doing the Haar average. And then this calculation then corresponding you calculate the variance of that average. And then if the variance is very, very small, then you say the average result should be typical result indeed. And that's the statement of typicality. But in general, when you go to finite temperature, or when you go to a system with an infinite dimensional Hilbert space, or when you go to field theory, and there's no such average you can do. Since there's no such kind of canonical average you can do to get such an answer. And then this just provides a self-consistent approximation. This just provides a self-consistency check that this approximation is self-consistent. Yeah, but here you don't have to do any average. In the case, so you can do the average, then it's similar to the typicality argument. Yeah.
Oh, sorry, can I ask a quick question? Here, these are the conditions that would make it, that would justify throwing this away. But it's not clear when this would be satisfied. Or
you mean the you mean when? You mean the at what time, or for what kind of systems?
Both.
Yeah. Right. You just say in terms of at what time, you said you want the system to have sufficiently the input here we don't worry about the question, when does the system thermalize? We just assume the system have already thermalized.
I see.
Okay. Yeah, so this is the input. So we assume a system already thermalized. And then, yeah, then for your second part of your question, you're asking when for what kind of system or what kind of observable this may apply. Yeah, then this you have to check self-consistently. Say you can say for the case of the Renyi entropy, then that will, then this argument just shows that this will apply generically to any system which have thermalized, and this D1 is sufficiently large.
Okay, I see.
Okay. Yeah, and then you can also try to apply the same procedure. Yeah, because this procedure you can apply to any observables which involving the replica, involving doing some kind of replica. And then for each observable, then you can try to check whether this is self-consistent. And if it's self-consistent, then that gives you confidence that this approximation might be good. And if it's not self-consistent, then of course this approximation will not be good. I will mention some more examples a little bit later. Yeah.
I see. Thank you.
I have a question.
Is it possible to make the statement more precise? Can I say that for all systems satisfying, for example, ETH, this approximation applies? Can I say that?
Yeah, I don't. So I don't know direct connection to ETH. So this could be weaker. Yeah. So saying certainly for systems satisfy ETH, I would expect this to apply. But this may apply.
You prove that certain assumption to the Hamiltonian will lead to this approximation.
No, we don't have a proof, but indeed we expect some kind of derivation should be possible. And yeah, this is something we are thinking about right now, indeed. And indeed, one possible, say, a way is to say if you assume the system satisfies ETH, whether you can derive this. Indeed, I think that might be possible. But I expect even maybe with even maybe weaker assumption, you can already derive this. So assuming ETH might already be too strong. Yeah, not too strong, maybe just strong. You might be able to have a weaker assumption to be able to show this. Yeah.
I see. So at the moment, so this looks like a expectation, right? The approximation, and
that's right. That's right. Yeah, okay. That's right. This is a self-consistent expectation. That's right. Yeah.
I see. Thanks.
The previous slide, please.
Okay. Yeah.
Yeah. So here, the last paragraph, if we take tau equal to E, that's the original Hawking's suggestion, right?
Yeah, that's right. Yeah.
Yeah, but it has a problem which violates unitarity. Then my question here, can you show that if we sum over the permutation, all permutations, then the result does not violate unitary?
That's right.
Only expect unitarity is not violent.
Oh, you can prove that. Yeah, I'm going to show that in a couple of slides. Yeah, you can prove that.
Okay.
Yeah, good, yeah. Good. Yeah, so actually, I think maybe just in the next slides. Yeah, so the general, now let me just describe some general features of this result. And so in the limit of the large system, then you find that the information of your initial state have dropped out. And indeed, that's what you expect, because when you approach equilibrium, you forget your initial state, okay? And but the non-trivial thing is this permutation, okay? So you sum over the permutation, so I can write this as the sum over Z and for each of them. So now you can check that. Now you can just prove that when you sum over permutations, then these unitary constraints are all satisfied. Okay, are all satisfied. And also to give you some intuition, there among all these permutations, there are two particularly simple contributions. So the one, of course, is just corresponding to the identity. So when you take the identity, essentially, as I mentioned, this eta and the E, they are just some way to tell you how to take the traces, okay? So now when you take the tau to be E, then you find, and this just gives you essentially the Renyi partition function of the equilibrium density operator applied to A, okay? And then what you get is just the Renyi entropy for the A for the density operator. Yeah, then indeed that would be the original Hawkins approximation. But now if you include the eta, so remember the eta is the one, another special one I mentioned before, corresponding to n go to n-1 and n-1 go to n-2. So for this eta, then you find this actually corresponding to the Renyi partition function of the equilibrium Renyi partition function of the A bar, okay? And then for other permutations, then we are involving more complicated trace structure when you take the trace over this I alpha. And so that does not have such simple interpretation anymore. Yeah. So, but in the case you can also prove when one of A or A bar is much, much smaller than the other, then in this case, then one of them dominates. Okay, just either E dominates or eta dominates. All the others are subleading. And then the Renyi entropy for A just given by the minimum of this. Then of course in this case it's also manifestly satisfy the unitarity constraint. And this is also indeed what you intuitively can guess just from the Page's result. So the Page's result is the case for the infinite dimensional Hilbert space with no energy constraints. And but now this just applies to any systems, okay, even to field series, and then this result apply. Okay, yeah. So this is something you can intuitively guess, but here we actually have a derivation. Yeah. Good. So another feature, yeah. So now if you look at this quantity, now you can try to, let me try to give you some intuition how you estimate the size of each term. So you sum over tau, right? So so let me tell you a little bit how to estimate the size of each for each tau term. So this contraction essentially just corresponding to you taking the trace in various different ways, okay? And for example, for E it means you take the trace this way, and for the eta you take the trace in this way. So for tau equal to E, then you have n A bar traces, but only one A trace. And in this, for eta, you have n A trace and one A bar traces, okay? So essentially they just give you different trace structure. So in general, if you look at general tau, you will have some number of A traces, some number of A bar traces, okay? And now, but then it's a simple result. You can show that the number of A traces is related to the number of cycles of tau, okay, which I can denote by k tau for this permutation tau. And the number of A bar traces is the number of cycles for eta minus 1 times tau, okay. And now, if you just heuristically, you expect that when you take the trace, and the trace give you the effective dimension, say, of that subsystem. Okay, so if you take trace over A, it gave dA. Say dA here just means this, some effective dimension of A subsystem. If you have a finite dimensional Hilbert space, that would be just the dimension of the Hilbert space. But if you have an infinite dimensional Hilbert space, then this would be just some effective dimension. And the setup is guaranteed this should be finite because the I alpha have a well-defined trace. Anyway, so now by counting how many traces you have, and then you can just find, and also the relative size between dA and dA bar, and then you can just estimate the magnitude of each term. Okay. And for example, just a generic term will have this structure. So dA to the power k eta minus 1 tau, and dA bar to the power this power. Okay. And then from here you can decide which one dominates. Okay. For example, when dA is much greater than dA bar, then you want to maximize this power. Yeah, I might have switched the index. Maybe here should be k tau, here should be k. Yeah. Anyway, you just now you can just say if dA much greater than dA bar, you want to maximize this exponent. Okay. And but in the case which dA is comparable to dA bar, then you want to maximize the sum of the two. But then you can also show that the sum of the two satisfy an inequality. They're always smaller than n plus 1. Okay, small, and this equal sign can be saturated, and the equal sign is saturated for permutations which are in one-to-one correspondence with so-called non-crossing partitions. Yeah, so I want to explain to you the what is the non-crossing partitions. Mathematically, it takes a couple of minutes, but it's not it will not be very important for us. Anyway, just for subset of the partitions, and then you find that this is saturated. Okay, and then when dA and comparable to dA bar, and then you want to consider then those taus corresponding to non-crossing partitions will dominate. Okay, will dominate. Anyway, so you can actually represent this trace structure diagrammatically, and you can draw the double line notations corresponding to here. Yeah, because you have A subsystem and A bar subsystem. So since contraction related to A subsystem and then denoted by the solid line, and the contractions related to by A bar subsystem then corresponding to the dashed line. And then the solid line cycle, a solid line loop just corresponding to a trace for, say, for A. And then the dashed line loop then corresponding to a trace for A bar. Anyway, now from this kind of double line notation, you can just read how many traces each of them have. And then the non-crossing partitions, then here just can be seen as the planar diagrams. Okay. And the planar diagrams then saturate this equality, and then the non-planar diagrams then corresponding to crossing partitions. Good, and then one final thing let me mention. So in the case which I alpha itself can be represented by Euclidean path integrals, and then you can actually represent this thing also by Euclidean path integrals. And now just you have. Yeah, now you can just express this in terms of the Euclidean path integral for the n replicas of I alpha. So remember, the original Lorentzian path integral has 2 n copies of the original system. But once you do this approximation, now become n replicas of your equilibrium density operator. Okay, and so each tau just tells you how to do the contraction between different replica copies of I alpha. So you have n replicas of I alpha, and then this tau just tell you how to do the contraction between them. So for tau equal to 1, E just corresponding to the standard contraction for the Renyi entropy for A, and the tau equal to eta corresponding to the standard Renyi entropy contraction for A bar, and then for others you have other more general things. Okay. So let me just give you a very simple example. Say at finite temperature, finite D at infinite temperature, then the I just given by the identity, and the Z equal to D. And then in this case, let's consider the most interesting regime is that the D and dA bar are comparable. So their ratio is finite, but each of them is very large. So in this case, you need to sum over all planar permutations. Okay, all these non-crossing permutations. Essentially sum over all planar diagrams. And then you find all the sum of all planar diagrams can be captured by this number called Nairn number. Corresponding to the number of non-crossing partitions of n objects into k subgroups. Anyway, the details is not important. yeah, but the key thing is that in this case, you can easily sum over all planar diagrams. And yeah, good. Any questions? Yeah, let me check the time. Sorry, how I'm doing this time.
5 minutes over, but that's totally fine.
Oh, sorry. Yeah. I didn't realize already takes so much time. Okay, yeah, good. Let me try to speed up a little bit. So now you can apply to gravity system. And so this procedure is very general. It applies to all quantum mechanical systems, including quantum gravitational systems. And so essentially now you just reinterpret this as the amplitude of gravity, okay? And so this approximation is just a pure, it's a gravity, it's an approximate, it's an equilibrium approximation at the quantum mechanical level, okay? So we are not doing any approximation in gravity itself yet, okay? So when you apply this to gravity, so then you should interpret this overlap as the amplitude in full quantum gravitational theory, okay? And then in specific gravity theory, you may want to approximate this using say a semi-classical approximation, etc. But as defined, when you apply to gravity, this should be interpreted as the full quantum gravity. Anyway. So if gravity respects the usual rules of quantum mechanics, then the prescription should lead to answer consistent with unitarity, which is manifest unitarity. And now, if this I alpha have a Euclidean gravity path integral interpretation, and then now you can, as we mentioned before, now you can just rewrite this as the Euclidean path integrals, okay? And then this can be implemented at the semi-classical level using Euclidean path integrals, but still get an answer which is compatible with unitarity, okay? And then for holographic systems, the boundary version of the prescription then provide the boundary conditions for formulating the prescription for the Bach gravity. And so intuitively, this leads to couplings among different replicas. So that could lead to, say, replica wormholes and geometries connecting different replica universes. Okay. So now let me give you yeah. But let me just emphasize, even if you are able to calculate this overlap using exact quantum gravity amplitude, this is still approximation. Okay, this is because this is approximation already at your quantum mechanical level. Good. And so now let's consider just a simple model of the black hole evaporation. So now let's consider a situation where the initial state actually describe a star, which under time evolution collapsed to form a black hole and subsequently emits Hawking radiation.
A question, so can you go back one slide?
Yeah.
So what's the meaning of the full quantum gravity theory here?
Yeah, you just say,
do we have such a theory or?
No, I'm just saying, I'm saying just there's various level approximation here. So whenever you write down such a answer, you're already doing approximation, and that approximation have nothing to do with gravity. So this approximation have nothing to do with gravity. So even if you can calculate this quantity using exact full quantum gravitational theory, you are still doing approximation. Okay, and now of course we don't have a full quantum gravitational theory. So in practice, then we approximate. Then in practice we will approximate this quantity further using semi-classical method.
So I mean, this result actually, you always have this result regardless of what kind of full quantum gravity theory at the end it might be. Do you mean that, or?
That's right. Yeah, what I mean is the following. So later when I talk about this black hole evaporation model, and then people observe that somehow there's some kind of non-factorization issues, etc., which people suspected that may have to do something with something with the ensemble average of the boundary theory, etc. But but I want to emphasize later that whether those things have to whether those issues have to do with the semi-classical approximation in gravity. What I emphasize is that there are certain things which have nothing to do with semi-classical approximation, just are related you're doing this approximation. Yeah.
Okay, thank you.
Yeah. Good. Okay, so let's look at this simple model, and then the first, let's just imagine the time is big enough that the black hole have already evaporated for quite some time. Okay, and so of course, the black hole evaporation is not strictly speaking, it's not an equivalent process because black hole is still emitting thermal emitting radiation. But the black hole radiation process is sufficiently slow that we can consider as a quasi-equilibrium process. Okay, so the time at each the state at each time can be approximately considered as equilibrium state. Okay, so that's
sorry. Again, a question about last slides. Sorry. So when you view this Hamiltonian evolution to be on the boundary, to be suppose this is a holographic gravity system, and on the boundary, but then the replica will be the replica on the boundary.
That's right.
But usually the replica wormhole is the replica in the bulk.
That's right. So, Then the replica on the boundary then can be used as the boundary condition to construct the replica wormholes in the bulk. Because
is that equivalent, the replica wormhole in the bulk corresponding to a replica on the boundary? Is that?
No.
I don't think. No,
that's not what I meant. No, what I meant is that in the boundary, there's a certain replica procedure, okay? Tell you how to do this tau. And that provided the boundary condition for you construct your gravity path integral. And the result of that gravity path integral then give you the replica wormhole.
Right, but it's
okay. I think that this will be clear if we go the next couple of slides, and then if you still have questions, then
okay.
Because I'm going to make this more explicit.
Okay.
Okay, good. So the anyway, so for simplicity, we will take the radiation subsystem to have a finite dimension, have dimension n, and there's no energy constraints. So the equilibrium density operator for the radiation subsystem will be just identity. But the black hole part we take to be the thermal, to be some thermal density. For example, just the thermal density operator with some inverse temperature. Okay, so the full equilibrium density operator will be, say, unnormalized will be the identity corresponding to the radiation, and some thermal density operator corresponding to the black hole. And so also I will assume, just this related that this black hole have a very large entropy, so that the black hole partition function contains of entropy part, and then a part corresponding to some partition function. So this is just some general structure you assume for this. Okay. And then with this setup, then one interesting regime is just when these two become comparable. Okay. When one of them is much larger than the other, is corresponding to a simple, is much simpler. And when these two become comparable, then you have to sum of all planar diagrams. So in this case, we just sum of all planar diagrams, and then our procedure just give you an answer. Okay. So this answer is a little bit complicated. You don't need to know its detailed structure. Anyway, just to show you that there's a really straightforward procedure. Once you write down the setup, and then you can just write down the answer. And the key point of the this final answer is that just the Renyi entropy or the Renyi partition function for the radiation, and now just expressed in terms of various, say the dimension of the Hilbert space of itself, and then the partition function of the black hole part. Okay. Yeah, just the density operator of the black hole part, say raised to some power, and this Zj corresponding to power. Anyway, if you load the density operator for the black hole, and then you should be able to calculate all these different moment, etc., and then you can just get this. Good. So so yeah, and now let's consider the specific model considered by this Stanford group, which they consider the special or 1+1 dimensional in this JT gravity. Yeah, so so in their theory, it's a black hole. Then there's the end of world brane, which I use the green line. Yeah, the details of this end of brain, the end of the world brane is not important. The only thing, yeah, so this is the Euclidean picture, and the only thing that's relevant is that the equivalent density operator can be written as the standard thermal one, and then a part corresponding to this the end of world brane part, okay, which I called it F. Okay, and yeah, so that's only input. Say in addition to the thermal one, you have the part corresponding to this the end of world brane. And now you can just write down this replica, okay? So, so according to this procedure, you need to compute this kind of quantity, okay? You need to compute this kind of quantity, and then from the boundary path integral, you just doing such a path integral, and so each the solid arrow corresponding to exponential minus beta h, and this green dot corresponding to this this f. And now this provides the particular, so this is how you should do the path integral in the boundary theory, okay? And now use ADS-AFT or use whatever duality, you can translate such a boundary condition into how you should do the gravity path integral, okay? So and then you essentially just feel the gravity. Yeah, essentially the Bach manifold should be some manifold with this as the boundary condition, and then you just find the saddle point of the Bach manifold. Okay, saddle point of the Bach path integral, and then that gives you the gravity calculation of this quantity. Okay, yeah, because in the boundary, yeah, this gives you the gravity. Now this gives you the gravity calculation of this quantity. And now you can just, yeah, just do this, and then you find that these two derivation of this prescription of replica wormholes introduced by these people, yeah, and actually provide the precise prescription when and how to introduce such kind of replica wormholes. Okay, so in their discussion was more like some kind of ad hoc prescription. You try to get the unitarity invariant answer. But here it's guaranteed you get unitarity invariant answer. So physically, these replica wormholes, yeah, physically this shows that these replica wormholes can actually arise in systems with a fixed Hamiltonian with no average needed. So here the approximation applies really to a system with a fixed Hamiltonian. Okay, there's no, we are not doing any averages, and we are just doing an approximation. So in particular, as discussed in that paper, which I will not discuss in detail here, we discuss in detail in our paper, is that they have some factorization issues when they look at the matrix elements, say of the, say when you do this replica wormhole for the matrix element, and then you don't get the same answer when you do the matrix element of the Renyi entropy, and then they see some kind of contradiction, non-factorization issue, etc. Then they speculate that may be related to you have to do some kind of ensemble average over the boundary, etc. But here we show that actually there's no average needed. In particular, this kind of non-factorization issue have nothing to do with whether you are using the semi-classical approximation or not. Have nothing to do with whether you use semi-classical. Even if you do the exact quantum gravity calculation, to do such kind of replica wormhole, you still will get such kind of factorization issue. Anyway, so this method also explains the emergence of Euclidean gravity in describing entanglement entropies of a pure state and why it's compatible with the unitarity. And so in some sense, there's no magic. Somehow the Euclidean gravity can be used to describe the unitarity, to give an answer which is compatible with unitarity. People always say, oh, there's some magic somehow. Somehow the semi-classical Euclidean gravity seems to know the unitarity invariant answer, but here we see actually there's no magic. There's a precise prescription you can follow, and then also this calculation also illustrated the mathematical structure underlying this Stanford group paper, which to be the permutations in particular is non-crossing permutations, which underlies their calculation. Okay. Good. You can also apply this to black hole, internal black hole coupled to a bath, and then you get the similar result. Then again, there confirm. Yeah, you just rederive the results. Again, it's ad hoc prescription people proposed. And they're just involving you do various different kind of contractions of your different replica. Euclidean replica manifold. Good. So you can also apply to other systems. For example, rather than collapsing, rather than the evaporating black hole, you can just consider, say, a big black hole in ADS formed from gravitational collapse, and then you can try to calculate the Renyi entropies. And then you need to sum over various kind of permutations, etc. Yeah, again, this provided the boundary conditions how you should find the box saddle points for the calculation. Okay, so let me try to summarize. Yeah, so here we always assume that U can take a far from equilibrium state to equilibrium. And then we also assume that we can ignore this dq, okay? And so it would be nice to be able to characterize precisely what U will lead to the above, these two above assumptions, okay? Say whether chaos is enough or whether this can also apply to some integrable system, because some integrable system, they also thermalize. They can also equilibrate, okay? And also if indeed somehow the chaos is responsible for this, then what aspect of quantum chaos is responsible for this? And so let me here just quickly mention a related result. So we can actually show that this equilibrium behavior of the Renyi entropy can be considered as a special case of the general dynamical properties of operator growth. So the Renyi entropy just related to the, you start with some initial density operator, but you can also consider some general operators, okay, not a density operator, just some general operators, study the Heisenberg evolution of such operator. And then again, you can derive very similar results. And in particular, in the previous paper, we discussed a process called the random void distribution. And we showed that this random void distribution actually is essential for to get unitarity, to get answer responsible for the to get answer which are compatible with unitarity. And so in a sense, this random void distribution somehow is very close related to somehow you have to sum over other permutations. Okay, you have to sum over other permutations. Anyway, so let me just conclude. Would be nice to understand the part of the property of the part we dropped. Also, we expect that somehow the time scale that this equilibrium approximation should apply should be sufficiently long time, but not too long time scale. Okay, so we want the system to thermalize, but not too long time scale that the fluctuation around the equilibrium becomes significant. For example, certainly not the exponential time scale in terms of the entropy. Okay. And you can also apply it to some other, say, observables. So you can look at correlation functions. So now you can show that, suppose that all these time scale happen after the system have thermalized. If say Ts is the thermalization time, so if all this time happens after the system have thermalized, then you can just approximate this by the thermal correlation functions. Okay. Provided that suppose A is the smallest subsystem, including the product of all O's, and if A is sufficiently small, say A is smaller than A bar, and then this approximation is good. Now, otherwise, if A is comparable to A bar, then you find that this self-consistency condition I mentioned earlier breaks down, and then you can no longer trust this. Okay. Also, finally, let me just mention a very trivial example. Say if you consider, say, just trace U and trace U deck to the power n. And so this is already a factorized. So in this case, there's no initial state, there's no equilibration, but still there's 2 n copies of U, so you can naively apply this equilibrated, you can naively apply this approximation, okay? And then if you indeed apply this approximation, and then you find that this can be written as in the replica space as trace in, so this trace is in the 2 n copies of your Hilbert space, just taking the trace of the evolution operator. And then again, you can separate into ZP plus ZQ. And now you find that DQ actually is not suppressed. Okay, so now you can actually find that the self-consistency condition is violated. Okay, and this quantity has been used very, very often to study the discreteness of the energy level. So if you wait the time long enough, and then this gives you the form factor which can probe the discrete structure of the energy levels. And so let me just make a side comment here that the gravity description to calculate this quantity also involves some kind of Euclidean wormholes, okay? Some kind of Euclidean wormholes connecting different boundaries. But we see actually for this quantity, actually this equivalent approximation actually breaks down, okay? And actually does not apply. So this implies that somehow this kind of Euclidean wormhole, which apply in different contexts in gravity, actually they may have very, very different interpretation from the field theory point of view. Okay, from very field theory point of view. Yeah, so let me just stop here. Yeah, thank you. Yeah, sorry for going over so long. Yeah.
Not at all. We would like to thank Professor Liu for giving a very beautiful talk. So people, if they have questions, please continue. I have to pack for the moment just because the room that we are in will be taken shortly. But Muxin will help us to continue chairing for the moment as I move my computer to a different place. Sorry about that. Please, people, please ask questions.
Okay, so is there any question and comment for Professor Liu's talk? Okay, well, I have a question. So here, so the key point basically is you apply the approximation by neglecting contribution from Q, right? And then, but since we know that for page curve in the end, the entropy goes to 0. So your results seem to suggest that the page curve in the end, well, should have a small tail, which is related to the Q contribution, right? And
so for the page, for the time, let me say if you study, say, ZQ for specific situations, equations, then you will see that ZQ, so you will see that ZQ actually exponentially decay with time. So if you say exponentially decay with time, so become very, very small at the late time. And so the page curve is also about the leading order results. Yeah, because when you calculate, say you for many body system, you always have to take some kind of limit of the system is very large, and you always neglect some kind of small pieces. Yeah. So there's no. This does not mean that the page curve have a small. Yeah.
But the ZQ, but how can I see the ZQ exponentially decay when time goes?
Oh, yeah. So this we don't know, but we can study some special examples. So we can study some examples. For example, you can calculate ZQ, or for some simple cases. For example, using some kind of Brownian circuit, etc. Then you can actually calculate ZQ explicitly for some quantities. For example, the second Renyi entropy, then you find it's actually exponentially decay. With time.
So you applied some this technique to certain specific Hamiltonian and show that ZQ decays exponentially. That's what you.
That's right. That's right. Yeah, for certain systems, you can actually calculate the whole thing explicitly, including ZQ, and then you can see that ZQ actually is suppressed. At long time. Yeah.
I see. Okay. Thank you. So
I have two questions.
Oh, okay, please.
The first one is the following. In the title of your talk, you emphasize the pure state. In your formalism or in your computation, does the pure state condition for a mixed for a density matrix play any role?
Sorry, let me just try to understand your question. You're asking if you start with initial density operator, will that be different, or is that your question?
My question is, in your whole discussion, including the framework, where have you used the pure state condition for density matrix? That's rho squared equal to rho.
Yeah, good. Yeah, we did use it in this step, which I suppressed. So so when you say let me just go back to these slides. Right. Yeah. Right. So indeed, in this, I should have written one more equation, then become clearer. So when you look at the ZP term, so ZP term just corresponding to, you replace this U dagger power m by this P alpha. Okay.
Okay.
Okay. Yeah, by P alpha. And now in this expression, you still depend on rho zero. And now you have to contract with rho zero with the P. And now in this step, then you find actually when rho zero is a pure state, and then the contraction just become an overall prefactor. And then all the rho zero dependence just become an overall prefactor, and essentially change this prefactor to 1 over z to the power n. And just reduce to this form. But if you have a density operator, and then actually part of the information of your original density operator still remain.
Mm-hmm.
The density operator don't decouple so cleanly. Yeah.
Okay. Thank you. My second question is the following. I think in old days when Hawking argued for the information loss paradox for the black hole.
Mm-hmm.
He emphasized that a principle of quantum mechanics is that the unitary, a unitary theory cannot turn a pure state into a mixed state.
Mm-hmm.
Right?
That's right.
I mean,
yeah.
Historically, now it seems to me that the paradigm, if I use this terminology, okay, has been changed. So then my question is, if we look back in retrospect, we would say Hawking's argument was wrong, or Hawking radiation actually is somehow or in certain way circumvented.
Yeah. So yeah, indeed. So the key point is the following. So the Hawking's argument was that, say, indeed, the quantum mechanics pure state should remain the pure states.
Right.
But now, if you look at the final state of the Hawking radiation, then he argued that the final state of the Hawking radiation should be thermal, and then looks like you have evolved from a pure state to a mixed state, and then somehow quantum mechanics must be violated.
Right.
So now what we realize is that we find ways to show that the final states indeed satisfy the unitarity constraint of the pure states. So we have found support that the final state is actually indeed is pure. So you haven't evolved into a density matrix. Yeah.
Okay. So actually, your then what's the key point here to solve the black hole information paradox? I mean, in your derivation.
Right. So yeah. So the whole difficulty is so Page pointed out in 1973 that if the black hole, Page formulated the following question. Page said if the black hole evaporation is unitary, then the final state must be pure.
Right.
Then we must be able to see this unitarity constraint when you calculate this entanglement entropy or the Renyi entropy for the for the radiation.
Okay.
Then should satisfy this constraint. And so for a long time, so Page formulated this as a challenge, but people could not really calculate that.
Okay.
So people really could not calculate that, even say I would say both in field theory or in gravity, just even in general quantum many-body system, if you want to calculate the Renyi entropy, say of an equilibrated pure state, and to show that it satisfies unitarity constraints, has been a very difficult question. The only trick is what I said earlier, is that you do the hard average for finite dimensional Hilbert space. And there's no efficient way to calculate it. And so what has changed? Yeah, in gravity is even more so. So in gravity, people, so this was the challenge people did not know how to meet.
Okay.
And then these recent papers of last year, which they indeed were able to calculate this quantity using gravity, using some kind of semi-classical path integral methods, and then somehow they show that indeed they're compatible with unitarity.
I see.
And then our method is just to show that actually there's a general way to do this for general quantum mechanical system, and then the prescription people did, people calculated using gravity this new new way to calculate the gravity, then follow from this general quantum mechanical method. Yeah.
I see.
Yeah.
Okay. Also, yeah, a small question. The double thermal copy actually is related to the K-dish is closed path green functions. Is that right? You first involve time from 0 to from minus infinity to plus infinity, then you go back. It's called
right.
closed path.
That's right. The thermal field double is actually more general than the K-dish.
I see.
So because in the thermal field double, so the K-dish, you have a specific path ordering,
right?
And thermal field double just specify a state for you, and within that state you can do arbitrary ordering, and then indeed.
I see. Okay, I see.
Yeah, for some subset of ordering in thermal field double, precisely corresponding to K-dish. Yeah.
Okay. Okay.
Yeah.
Okay, very good. Thank you.
Okay. Yeah. Thanks. Yeah.
Can I just ask one more question?
Sure.
So is it right to say that it's not yet completely clear what are the observables that we should compute to exactly see that the state must be pure in the context of gravity? As in, in the discussion in your talk here, it's not immediately clear what expectation values of which observable I should look into to be able to tell the difference from a mixed state.
Yeah, that's right. So this entanglement entropy and the Renyi entropy are special. Somehow they satisfy very simple unitarity constraints. But now if you say, let's look at some correlation functions. So if you look at the correlation functions to tell the difference between a mixed state and the pure state, it's much more difficult. Because you can calculate some correlation functions in the pure, say you can calculate correlation functions. Even if you see some deviation from the thermal behavior, you can say this may not be exact thermal behavior, but you cannot say this is a pure state. So from correlation functions to be able to say, you are in the pure state is much more difficult. Yeah, indeed. So somehow the entanglement entropy and the Renyi entropy, they have this kind of very nice properties that the unitarity constraint can be seen in the simple way.
I see. So maybe I should just think of entanglement entropy or Renyi entropy is the observable in some sense that I should look at, and I'll be able to tell.
That's right. Yeah, so certainly it would be nice to find other observables too, find other observables too. Just say if you look at correlation functions, these questions are very hard to formulate. Yeah.
I see. And one other question is the fact that so when we do the original Hawking radiation computation is sort of semi-classical, where a field where some matter fields lives in some background. But the resolution right now, it must involve summing over geometries of different topologies. So somehow the dynamics of gravity must be invoked in order to resolve Hawking radiation. Is that a fair statement? Or
yeah, but even before you have to use the dynamics of gravity. So the dynamics of gravity you always use. Just previously, somehow the Hawking's calculation essentially only included this identity contribution, and and then you have to include the other permutations. So in the simplest case, you only need to use including one other permutations. Just say somehow you have to include some other permutations in order to,
Okay, sorry. I think I'm good. Are there other questions?
I have another question. Okay. Yeah. So I don't know. Yeah, whether your method can be applied to the SYK model, showing that whether it's asymptotic behavior or asymptotic behavior for some range of times. I mean, the system, the pure state in that model can be evolved into some equilibrate, pure state.
Certainly. Right. Sorry. Maybe you finish. Yeah,
I finished.
Oh, okay, good. Certainly. This can be applied to SYK model, because we do know that SYK model, at least in certain regime, it should thermalize. So I think that this method is good, that it gives you universal results. So it actually applies to all systems. So does not care about the details of your system. Say whether you use SYK or some other strongly coupled quantum mechanical system, it just predicts the universal result. Only depend on how you characterize your final equilibrium state. So once you say if your final equilibrium state is described by the infinite temperature finite dimensional Hilbert space, and then there's just a universal result applied to all systems. And say if your final equilibrium state can be approximated by the canonical ensemble, and then again there's a universal answer which apply to all systems. Can be So it's can be used to derive universal results without knowing details of a system.
Okay.
Okay. So,
thank you.
Thank you very much. We had so many questions. If there are no other questions, then let's thank Professor Liu again. And we will be meeting him in a couple of weeks' time in our upcoming workshop. So hopefully we'll have more questions for Professor Liu. So thank you very much.
Okay, no problem. Thank you. It's a pleasure.
It's pretty late. I'm sorry. Thank you very much.
Oh, it's okay. It's okay.
Oh, thank you. Oh, okay. Bye.
Okay. Thanks. Bye.
Goodbye.
Bye.
Bye.